Okay, this video is for my 2020 AP test review question number 6. So the first thing is they're reacting some magnesium with some hydrochloric acid, and it's making this hydrogen gas, and it's bubbling up, and they're collecting it over water right here. So first of all, write the balanced equation. So we would have magnesium metal, so it's a solid, plus HCl, AQ. Okay, that's going to make magnesium chloride, which would be AQ, plus hydrogen H2 gas. Okay, balance the equation, 2 and 2, so you put A2 there. All right, write the balanced net ionic equation. So you cross off any spectator ions, but you can only cross things off that are AQ on both sides. So the chloride is AQ on both sides, and that's it. So you got magnesium solid. Remember, solids don't put any charge because they're not ions. Plus 2 hydrogen ions. And so you should put the charge of 1 plus, and that's AQ. Remember on the ions to put their charge on the net ionic. Okay, it gives magnesium, and it's AQ, so it's ions, 2 positive ions, AQ, plus H2, not an ion, so don't put charge, gas. Okay, that's the net ionic equation. Your equation should balance in terms of atoms and charge. 2 positive ones equals 2 positives. All right, a student reacts 2.8 grams of magnesium with excess hydrochloric acid. Calculate the moles of H2 that should be collected. So 2.8 grams magnesium. All right, step 1, change it to moles. 1 mole magnesium, and the molar mass is 24.31 grams magnesium. Okay, so after you change to moles comes the mole ratio from the balanced equation. So basically for every 1 mole of magnesium, you're going to get 1 mole of H2. So 1 mole magnesium, 1 mole H2. You do the math and you end up getting 0.12 moles H2. Okay, now the gas is collected at 25 degrees Celsius and 774.5 torr. How many liters of water vapor should be collected? Okay, so this is one where you're going to need to use the PV equals nRT. And so we want what V equals to, so we'll move P to the other side. So V is equal to nRT over P. Okay, so anyway, we'll just start plugging in. So V is going to equal to the number of moles. Well, we calculated that we should get 0.12 moles times R, which can be found on your AP chemistry formula sheet, but make sure you use the right one. So we have a pressure in torrs, so we're going to use the torr one, 62.36 liters times torrs all over moles Kelvin. Now the good thing about the gas law constant R, it tells you what every unit everything needs to be in. So our pressure will need to be in torrs and our temperature in kelvins. Okay, so times temperature. Well, right now we're at 25.0 Celsius. You got to add 273 to that, so that's going to be 298 Kelvin. So make sure with gases you're always working in kelvins. Okay, and then we're going to divide that by the pressure. But there's always one catch when you collect a gas over water, is you have to take the pressure that you collect the gas at, like in the lab, which is 774.5 torrs, and you got to subtract the vapor pressure of water, which they're going to give you that in the problem, which is 23.8 torrs. Remember, with significant digits on subtracting, you go by decimal places, not by numbers. So that's like 750.7 torrs. That's the partial pressure of the gas that you collect the hydrogen. Okay, so we take away the vapor pressure of water. All right, and so then we solve that and we get V equals 2.97 liters, and we go back and this has two significant digits, so I'd probably round it to 2. So V is equal to 3.0 liters hydrogen gas. Okay, the student actually collected 2.8 liters. What's the percent yield? So percent yield is equal to the actual yield divided by the theoretical yield times 100. And so the percent yield would be equal to 2.8 liters is what we actually got. That gives you that in the problem. Divided that by the theoretical, that's what we calculated. And you take that times 100. And it ends up being about 93%. Okay, in another experiment, H2S is collected by reacting iron 2 sulfide with excess hydrochloric acid using the same apparatus and lab conditions used to collect the hydrogen gas. Okay, draw the Lewis structure for H2S. Okay, so add up the valence electrons, 6 plus 2, that's 8 electrons. Our picture needs to show 8. Sulfur in the middle, hydrogen, hydrogen. Okay, then we'll add our lone pairs. Okay, 2, 4, 6, 8. That's the Lewis structure. What is the molecular shape of H2S? Well, it's going to be bent. All right, now a student notices that the percent yield of H2S is much lower than the percent yield of H2. Identify the intermolecular forces between water and H2. So let's do water and H2. Okay, now water is a polar molecule. Okay, so water is polar and H2 is nonpolar. Now, the attraction between a polar and a nonpolar, okay, and so basically you're going to have a dipole, because a polar molecule is a dipole, and the only force would be an induced dipole. Okay, when you have a polar and a nonpolar, so dipole, induced dipole. Okay, and then we're going to do water and H2S. Okay, so water is a polar molecule, and H2S is also a polar molecule. All right, and so now basically you could end up, when you have a polar and another polar, you could end up getting a dipole-dipole attraction. All right, you wouldn't necessarily have like hydrogen bonding, because with water, to get, like, here's water, and then if you had like H2S, H, S, H. Okay, now in order to have a hydrogen bond, you have to have a hydrogen sandwich. It has to be sandwiched between F, O, or N, and it's not, because you see it's S and O, not F, O, or N, the hydrogen. So no hydrogen bonding. So you would have a dipole-dipole attractions there. Okay, the forces between them. Now, use that to explain one reason why the student's percent yield of H2S is much less than the hydrogen's percent yield. Okay, so a dipole, induced dipole, this force of attraction is going to be very weak. And basically what that's going to make, it's going to make the H2 is going to be pretty much not very, almost insoluble in water. It's not going to dissolve very well. Whereas the water and the H2S, when you bubble the H2S in there, because it has a stronger dipole-dipole attraction, it's going to be very soluble in water. And so as you're collecting the gas, some of the gas is going to dissolve in the water, and it's going to basically go in between the spaces in the water, and you're not going to collect near as much volume, and that's why your percent yield would be much lower. Okay, now hydrogen sulfide decomposes according to the following reaction, which Kc gives you that, and if 0.29 moles, what is the equilibrium concentration of all species? So the first thing that I like to do is, hey, this is an ice table. Gives you 2H2 plus S2. So we'll make our ice table. These are all gases, so initial, change, equilibrium. So 0.29 moles, remember you got to put in molarities. So you take 0.29 moles divided by 3.0 liters, and that's going to give you a molarity of initially of 0.096 molar. So that's initially what we have of this. And we would have 0 of this and 0 of that initially. Now, this is going to go down by 2x. This is going to go up by 2x. This is going to go up by x. And so at equilibrium, we're going to have 0.096 minus 2x. We're going to have 2x, and we're going to have x here. Okay, so find the equilibrium concentration. So we're going to write the Kc expression would be H2 to the second power S2 to the first all over H2S to the second power. Now we know the Kc, so we'll plug that in. We'll just plug in our numbers here, 9.30 e to the minus 8 is equal to H2 at equilibrium, which is 2x, but we're going to square that, and we're going to multiply that times x to the first. And then we're going to divide that by this 0.096 minus 2x, and we're going to have to, let's see here, that's 2x, so that's going to have to be squared. All right, now one thing, because this Kc is such a small number, we can drop this x, we can get rid of that here. So basically then we're going to simplify it, so we're going to have 9.30 e to the negative 8 is going to equal 2x squared, that's going to be 4x squared, and then we're going to multiply that still times another x all over 0.096, and we would square that. So 0.096 squared is roughly 9.2 e to the minus 3. 9.2 e to the minus 3. Okay, so we'll combine like terms, and so we'll end up getting 4x cubed. So we'll get this. So we'll have 9.30 e to the minus 8 is going to equal 4x cubed all over 9.2 e to the minus 3. All right, now let me just solve this. So 9.2 e to the negative 3, and we'll take that times 9.3 e to the negative 8, and then we'll divide that by 4, and then we'll take the cube root of that. And so what I end up getting is I get that x is equal to 5.98 e to the minus 4. So I'm just going to round that off to 2 significant digits, I think is what I need. So 6.0 e to the minus 4. So that's what x is. So at equilibrium, s is going to be, this S2 is going to be 6.0 e to the minus 4. Take that times 2, and that's going to give you 1.2 e to the negative 3. That's going to be your H2 because you got to take 2 times x. And then you would take 0.096, subtract, and then you would take 2 times the 6.0 e to the negative 4, and you end up getting basically almost the same thing, but it's not going to be much different. So it's going to be, I'll just go 2 digits, 9.5 e to the minus 2 is what you would get there. Okay, now this one says if the temperature is decreased, how would that affect the concentration of H2 at equilibrium? So what you got to do is you got to go back and you got to look at this equation, and you see that there's a delta H here. Now that delta H is positive. That means it's going to go over here on this side of the equation. Okay, so it's on the left side. So I like to think about Le Chatelier's principle that, hey, if the energy is over here and you're lowering the temperature, you're taking that away, it's going to shift to the left. Okay, so it's going to shift left. Okay, you're taking energy away from this left side of the equation. So because the delta H would be on this side, and if you're lowering the temperature, you're taking energy away, so it's going to shift to the left to kind of replace it. That's how I like to think about it. Okay, if the volume of the container is decreased, so here's the volume of our container. So on this side of the arrow, and this is how you got to do it, you got to think of moles. On this side of the container, we have 2 moles of gas. So we have 2 moles of gas. On the right side of the container, we have 2 moles of S2 and 1 mole of S2. I'm getting that from the coefficients there. So I have 3 moles of gas. Okay, so if the volume of the container is decreased, that means if you decrease the volume, if the volume goes down, the pressure is going to go up. So if you decrease the volume, you're going to make the pressure go up. This reaction is going to shift, okay, to basically reduce that pressure. Okay, so if it shifts to the left, there will be fewer moles striking the side of the container. So it's going to shift to the left. Okay, that's how that would work, because it would make fewer moles and then would make the pressure go back to where it's supposed to be. Okay, that's it.